Hello everyone and welcome to this video. In this video we will be covering vectors for further maths A level as well as 3D lines. Let's get started. So first let's try to understand how 3D space works. 3D axes have a Z axis in addition to the regular X and Y axes we see in 2D, and this helps us represent how high up something in space is. Coordinates in 3D axes are represented using the following notation. So they have a Z component as well as the regular X and Y components we are used to seeing. Let's now represent a dot in 3D space using these coordinates. So we have a dot with coordinates 2, -3, and 1. So this is 2 units across in the positive direction on the x-axis, 3 units across in the negative direction on the y-axis, and 1 unit across in the positive direction on the z-axis. And note that the positive direction for the z-axis is up. And here is a general view of the 3D axes. Make sure to take great care when labeling the axes. Now let's talk about vector types in 3D. These work in 3D just as they do in 2D, where we know of 2 different types of vectors. The first is the position vector, which represents where a point is relative to the origin. And then of course we have displacement vectors, which represent the change in position between 2 different points. The calculation for the displacement vector is the same in 3D as in 2D, except we are also dealing with a Z component. Vectors in 3D are represented using the following notation. So they have the X on the top, the X component, the Y component in the middle, and the Z component at the bottom. Just to quickly recap how the displacement vector formula works. For the displacement vector AB, it is calculated using the position vector of point B, and then subtracting from this the position vector of point A. And of course, we will be dealing with this in 3D vectors. Now let's talk about forming 3D lines. Using both the types of vectors that we saw previously, we can define a line in 3D space. The equation for a line in 3D space is as follows. The direction vector d in the equation is not unique, and any non-zero multiple of the direction vector d will represent the same line in this equation. This is because the scalar lambda, which you might have noticed is right in front of the direction vector d, can adjust for this change in d. Now let's dive deeper into the equation that we just introduced. So we have r on the left-hand side. This represents a general point on the line. Then we have r0, and this represents the position vector of a specific known point on the line. And it can be any point. Then we have lambda, which is the scalar which scales the direction vector d. And then of course we have the direction vector d, which helps us define how the line looks in 3D. Now let's consider how this 3D line is formed using an example. Here we have the coordinate from earlier, 2, -3, and 1. And we have another coordinate, -1, 2, and 3. Between them we can form a direction vector. And if we halve this direction vector, we can get the midpoint with the coordinates seen on the screen. But if we multiply this direction vector by any real number, we could get any point that is collinear to these 3 points that we have just introduced, thus forming a line. Of course, here is how we derive it. We use the displacement vector notation to find the direction vector, and then using the formula, we can find the points on the line. And in this example, we will find the midpoint. Since the direction vector represented the 2 furthest points in our example, lambda being a half will represent the midpoint in our example. And yes, since lambda can be any real number, the equation will define a set of points. And this set of points will have A on it, which was 2, -3, and 1. And these points will also be in a direction parallel to D. So we can see the displacement vector and direction vector D on the screen. Note that the line equation would still work and define the exact same line if we use another point. So for example, if we defined R0 to be equal to M, as seen at the top of the screen, the line would be exactly the same. And the same would hold if it was the other point, which we had shown in our example visually earlier. Now this was one way we can form the line equation. There is another way of forming the line equation, which is known as the Cartesian equation of a line. And this is a different way of writing the line equation, which conveys the same information. So we can derive it here, using the initial equation and defining some general points. So defining R, R0, and D. We can form the components and then rearrange for lambda. And then we can equate the three expressions, since they're all equal to lambda, to get this general expression for lambda. And this is another way of representing the line, known as the Cartesian equation. Now you may wonder what will happen if, for example, one of the direction vector components is equal to 0. And then what will happen is you do not write it in this form. You do not write the equation over 0, because this will of course mathematically not be valid. However, you would just write that it is equal to the appropriate component of the R0, the initial point that we had on the line that was defined. So for instance, if D3 was equal to 0, then you would write the equation as normal, of course, assuming D1 and D2 were not 0, but assuming D3 was 0, then you would just write equal to A3, because as you can imagine, if the direction vector has a component of 0, then that component will not be changing regardless of the value of lambda. Now let's talk about the intersection of lines. Lines can intersect in 3D, but there are lots of possibilities where they may not. And unlike in 2D, lines do not necessarily have to be parallel to not intersect. These lines may instead be skew. And this refers to when lines are neither parallel nor they intersect. So let's consider some examples. So the first, of course, is where it intersects. The second is where it is parallel. As you can see, they're in the same plane, so they are not intersecting as they have the same distance between them. And then we have the skew lines. And a bit of a rotation of the 3D axes clearly shows us that they will never intersect. Now let's discuss finding the point of intersection mathematically. We can mathematically find the point of intersection between two lines, or if we do not find a solution, deduce that two lines do not intersect. So we can set up three simultaneous equations. You might realize that these will likely be of the separate components, so the x and y and z components of the lines. So these will make three simultaneous equations. And we do this using the two line equations. If they have a solution, they will intersect. Otherwise, they do not. And if two lines considered both have direction vectors that are multiples of each other, then they are parallel, unless both share the same points, in which case they are the same lines. So for instance, if R0 was equal for both, then they would be the same line, so they would always intersect in that regard. Let's go through finding the point of intersection mathematically using two lines. Here are the two lines from earlier that we showed intersecting. And we can define both of their line equations as follows. Note how lambda is different from u as they're two different scalars. We first find the components of each, and then we equate to them. So initially we had the x, y, and z components of the first line, and then we had the x, y, and z components of the second line. We then equated them together to form three simultaneous equations. We can now solve equation 1 and 2 to find values of lambda and mu, and then we must sub these values into 3 and check if it's consistent. Of course, if it is consistent, then we know that these values of lambda and mu are correct and there is intersection. But if these values of lambda and mu do not yield the correct solution for equation 3, then we can say that they do not intersect. So as you can see, we verify it here. Mu is equal to 1 and lambda is equal to -2. We could then use the initial equations and sub in our values for lambda and mu into the equation to find the point of intersection. As you can see, we did it for both and it worked. Now let's consider the skew line scenario. We will do the same thing and have the line equations of both, and we will find their components. Then we must equate them. And while number 1 and 2 do end up finding a solution for lambda and mu, number 3 must be false because 1 can never equal to -1. And therefore, the lines do not intersect and are skew. Note, if for 3 we had an equation in terms of lambda and mu, you would have to sub in the values for lambda and mu into the equation and see if it worked. Of course, in this scenario, that was not necessary as 1 is not equal to -1, so no substitution required. Now let's talk about a particular operation, the dot product, which is sometimes referred to as the scalar product. We use this to find the angle between two vectors. Let's see how this dot product is used. So if we define two general vectors, this is our formula. A dot B is the notation for the scalar product. And as you can see, it is just a multiplication of the corresponding elements of each of the respective vectors. So A1 multiplies with B1, A2 multiplies with B2, and A3 multiplies with B3. And then you just sum them up. For those of you who have watched the earlier videos, this is what the dot product is referred to when we were talking about using the dot product for matrix multiplication. The dot product has two formulae. One of them is the summation one, as you can see, where we multiply the individual elements of the two vectors and then we add them together. And then of course this is also equal to the magnitude of the first vector times by the magnitude of the second vector times by cos theta, where theta is the angle between the two vectors, as in the angle between the direction of the two vectors. And because of this, if A dot B is equal to 0, then the vectors are perpendicular, since cos 90 must be 0, as you will know from trigonometry. So this would make the entire dot product equal to 0. So if A dot B is equal to 0, then the vectors must be perpendicular. Now let's do this numerically with two vectors that we have defined here. We can find their magnitude and then rearrange to find theta. And of course we can display how this looks. Now let's talk about another operation that is done between two vectors, known as the vector product, or sometimes referred to as the cross product. We can use this to find a line that is perpendicular to two different lines that intersect. A line on its own has infinite possibilities for lines that are perpendicular to it. So it doesn't really make sense to try and use the cross product on a single vector. And the cross product also tells us the area of the parallelogram formed by the vectors using the operation. However, this is a fact that you will likely not have to use in your exams unless you are doing specific modules. Now let's visualize this. We have a single line with a line rotating around it about a point, showing that there are infinite possibilities for 90-degree lines around it. And then of course, we have the intersection of two different lines, as well as a line going through that point, showing that there can only be one possible line that is perpendicular to both lines. Now let's go about how to calculate the vector product. We can see this using the formula on the screen. So if we define two general vectors P and Q, P cross Q will be equal to the formula seen on the screen. Now this might seem a little bit complicated, but this is generally given in formula books, but you may be wondering if there is a way to do it without the formula booklet, and there is, using something known as determinant notation. So if we represent the vectors in a way that is like the determinant, we can eliminate rows and find the determinant of the remaining 2 by 2 matrix, and then calculate the element based off of this. So for the I component of the crossed vector, which will be formed as a result of crossing P and Q, we delete the row that has the I components, and then we take the determinant of the remaining 2 by 2. So we would do P2 times Q3 minus P3 times by Q2, which would be the determinant for a 2 by 2 matrix with these elements. And we could do the same for J and K, which will help us to derive the formula. Thanks for watching, and if you have any questions, feel free to drop them in the comments below. I hope to see you next lesson.